into W, BF divided by BW divided by BF, or 1 by BF by BW, nothing but we are having BW divided by BF, where BW is the breadth of the web or width, BF is the effective length of the beam. That BW value we are having 400 and BF value we are having 3040 mm. 3040 mm. From this we are having this value as, by calculating this we are getting this value as 0.131. 0.131. Top side and bottom side of the units are same, hence there is no unit. There are no units. From this, next we have to calculate the L by D max equal to how much L by D max we are providing and what is the provided deflection, that we have to calculate. That is nothing but L by D max equal to L by D basic into L by D basic into KT into, where KT is the reduction factor for based on tension reinforcement, and Kc into, where Kc is the factor for compression reinforcement, and Kf, where Kf is the reduction factor or modification factor for the ratio of width to the flange web. Okay, from this L by D max equal to, where L by D basic is the span to depth ratio for simply supported beam, we are having this value as 20, and KT is the percentage of tension reinforcement. This percentage of tension reinforcement, how we are calculating means based on the Fs value. That Fs value first we should have to calculate before calculating the KT value. That KT value, before keeping from graph we are taking this KT value. Before taking the KT value we should have to find out the Fs value. That Fs value, Fs equal to 0.58 into Fy into area of the steel required divided by area of the steel provided. Okay, I am writing here AST required divided by AST provided. Okay, if you see here, from this I am calculating the Fs. That Fs value equal to 0.58 into Fy, we are having 415 Newton per mm square, and the AST required value for applied moment, we are having this value as 2656.4 divided by area of the steel provided, we are having 3215.3. If you calculate this, we are getting this Fs value. That Fs value, it will be around 198.8 Newton per mm square. 198.8 Newton per mm square. Okay, from this Fs value, by using our modification factor for tension reinforcement, page number 38, if you observe here, the percentage of tension reinforcement we are having in between 1.2 1.6, and Fs value we are having in middle value, that means 145 below and 240 above. For this 1.5 corresponding to 190, where it is touching, that we have to calculate. If you observe here, in our present condition, it is touching at a point of percentage of modification factor as 1.19. The KT value, by using this Fs value, we are touching it as 1.19. It is not necessary to exactly coincident this value. It will be around based on our correct seeing value, that will be 1.19 to 1.18, 1.17. And Kc is the percentage of compression reinforcement. That the percentage of compression reinforcement we are not providing, that we are taking this value as 1.0. This Kc value we are only considering in terms of the doubly reinforced beam. Again, if you take the doubly reinforced beam, in doubly reinforced beam we are providing KT value and Kc value. Kf value we are taking it as 1.0. Again, in a singly reinforced beam, this Kc value, Kf value, we are taking this value as 1. We are only providing the KT value. These points you have to remember. And again, if you see here, this Kf value also we should have to keep. How this Kf value we have to keep means, if you observe in our code book IS 456 and page number 39, the ratio of web width to reduction factor they gave on curve, that linear line, and if you observe in our in between value 0.113, the 0.113, the corresponding linear line where it is going to imaginary touching, that point we should have to keep. That keeping value it will be around 0.78 by using 0.78. That means suppose if you see here the 0.131, that value for corresponding linear line we should have to measure. Otherwise I will draw the graph. If you observe in our IS 456 code book, this is the box, and these are the various type of lines, okay, various type of lines. If you see here, we are having values 0, 0.2, 0.4 and 0.4, 0.6, 0.8, and again if you observe in right side y axis, we are having 0.75, sorry 0.70, 0.75, and we are having 0.80, and we are having 0.85, okay, like that we are having. And again we are having one linear line. For this linear line, percentage of BW by BF, how much it is there, for the percentage of tension reinforcement where it is touching, that corresponding point we should have to find out from the graph. This is the rough diagram. If you observe in your code book, in x-axis the BW by BF value we are measuring, for that corresponding value where it is touching this linear line, that corresponding y-axis how much it is there, that value we should have to find out. Okay, this is the calculation for maximum deflection. That maximum deflection value, by calculating these values we are getting it as around 18.56. okay, L by D max we are having 18.56. this L by D maximum value we are having 18.56. Now we'll check our provided shear. Now we'll check for our provided deflection. The provided deflection is nothing but L by D provided. That means for how much length of the span is your beam and what is the effective depth you are going to providing. If you observe in our span, we are having effective length as 10-0, that means 10/450 divided by effective depth of the beam we are having in the beam is as 700 mm. That 700 mm, 700 equal to 10/450 divided by 700 equal to, we are having the deflection as 14.92. The deflection as 14.92. If you observe here, L by D max will be greater than L by D provided. L by D max will be greater than L by D provided. Hence our deflection is satisfactory. Hence our check for deflection control is satisfactory. Okay, I am writing here. Hence check for deflection control is satisfactory. Hence check for deflection control is satisfactory. Up to now, this is the design procedure for design of a T-beam. Okay. Again, these steps very speedily I will explain once. Okay. That check for shear reinforcement. Shear reinforcement from IS 456 2000 page number 72. Nominal shear stress tau V equal to VU by BW into D. From this tau V we are calculated. For calculated shear strength percentage of tension reinforcement we are providing. For provided tension reinforcement whether it is resisting or not by providing in the concrete, the tau C we are calculating. Here by table number 19 the tau V value exceeding tau C, but for that percentage of tension reinforcement. Suppose if you are providing more area of steel into the concrete, then in this condition tau B may not exceed the tau C value. I am providing percentage of tension reinforcement as 3215. Suppose I am providing 4000 mm square, there are chances tau B not exceeding tau C. That means tau C is greater than tau B. Then you need not to provide this balanced shear reinforcement. You can provide the minimum shear reinforcement. Okay, this is the spacing of the stirrups. We are calculating SV equal to 0.87 into Fi into ASV into D divided by SV. VUS, where VUS is the balanced shear stress. Okay, from this we are providing two-legged vertical stirrups with 8 mm diameter at a spacing of 400 mm center to center. Next we are having the check for deflection control. That check for deflection from IS 456 2000 PT and span BF by BW. I mistakenly write this value. You should not need to write 1 by BF by BW. Directly you can write this as BW divided by BF. That means ratio of width of the web to the width of the flange. From this we are calculating the L by D max with respect to the provided shear reinforcement. The provided shear reinforcement, if you observe here, this is the check for deflection control is satisfactory. Okay, next we are having the reinforcement details. The reinforcement details also I am sketching here. While writing in your examination, you should have compulsory use your scale to, or you should have to use your drafter while sketching this reinforcement. It is a design and drawing subject, hence you should have to write these sketches by using drafter in the your whiteboard of piece of the chart. Okay, I am sketching here reinforcement details. First I am drawing the longitudinal section. After that I will draw the cross section of the T-beam. Suppose if you observe here, this is the top surface of the concrete beam and this is the total gross depth of the beam. From this gross depth of the beam, I am providing here the longitudinal steel reinforcement bar in one side, that is in a compression side. Again one more longitudinal steel reinforcement bar in the bottom side. If you observe here, top side we are provided 2 bars of 20 mm diameter bars, and bottom side we provided the 4 bars of 32 mm diameter. To resist or to hold this longitudinal bars bottom side, we are providing some minimum number of bars in the top side. And again if you see here, from here to here we are providing the cover. That cover it will be around 50 mm cover we are provided for the beam. Again from this bottom also we are provided from this depth to this depth as 50 mm as our effective cover. Effective cover is nothing but from centroidal distance to the top of the surface of the concrete. And again if you see here, this is the reinforcement details. And again if you see here, I am providing the stirrup spacing. These are the stirrups which are holding in top of the longitudinal bars as well as in bottom of the longitudinal bar. These stirrups are nothing but two-legged vertical stirrups with 8 mm diameter at a spacing of 400 mm to 400 mm center to center. Again if you observe here, these are the bearing walls, or these are the supports for this beam. Again if you see here, this is also supports for the beam. The supports of the beam we are drawing here, and these supports are simply supported, and this simply supported with having thickness of 450 mm. The thickness of the beams we are having here 450 mm. And again here I am writing here, we are provided 2 bars of 20 mm diameter. 2 bars of 20 mm diameter in a compression zones. Again in bottom zone we are provided 4 bars of 32 mm diameter. In bottom zone, in tension zone we are provided the 4 bars of 32 mm diameter. Again if you observe here, these are the stirrups, and these are the stirrups. These stirrups we are provided a spacing of 400 mm. The steps we have placed it as 400 mm. I am writing here two-legged vertical stirrups. Okay, two-legged vertical stirrups, 8 mm dia, 8 mm dia at a spacing of 400 mm. At spacing of 400 mm center to center. At spacing of 400 mm center to center. Again, if you observe here, this is the clear span they are given in the problem. That clear span given in the problem as 10,000 meters. Sorry, 10,000 mm or 10 meters. And again, if you observe here, this is the effective span L effective. L effective they are given in the problem by calculating the effective span equal to center distance plus effective depth, or center to center distance between the clear span plus center to center distance between the support. That value it will be around 10,450 mm. 10,450 mm. This is the effective span and this is the clear reinforcement, and this is the total depth of the beam. The total depth of the beam we are having it as 750 mm. Total depth of the beam we are having 750 mm. Again, if you see here, this is the effective depth of the beam. Sorry, I am writing here the effective depth of the beam here. The effective depth of the beam we are having 700 mm here, 700 mm here, and this is the cover providing to the reinforcement bars. This is the longitudinal reinforcement details or longitudinal section. Okay, longitudinal section or longitudinal reinforcement details. Longitudinal section. Next, we are having the cross section of the T-beam. That cross section of the T-beam also we should have to write. In our examination, you should have to perform all these design steps and you should have to sketch this reinforcement details very neatly by using your drafter in the drawing paper. By seeing diagram only, they will give the maximum marks. Okay, the cross section of the beam I am drawing here. If you observe here, this is the T-beam, and if you see here, sorry, this is the cross section of the T-beam and this cross section. Okay, and if you see here, we are providing here a bottom side, that means in tension reinforcement we are providing 4 bars of 32 mm diameter. These are the 4 bars of 32 mm diameter, and in our top side we are providing 2 bars of 20 mm. 2 bars of 20 mm. To hold this we are providing the stirrups to the beam, and the stirrups are doing, these are the link up bars. And again, if you check here, this is the from this step to this step we are having, this is as our total depth of the beam. The total depth of the beam as we are having 750 mm. Again, if you see here, the from top of the surface of the concrete to the centroidal distance, I am writing the centroidal distance. The centroidal distance as D equal to 700 mm. This is the effective depth of the beam. Again, if you see here, these are the 2 bars of 20 mm diameter. 2 bars of 20 mm diameter. And the effective span here, this is the effective span of the beam. That effective span of the beam is nothing but 3040 into mm. 3040 mm. That is the effective width of the plane. This is the cross section of the T-beam. You should have to write very clearly in your examination. Okay, I am writing here cross section of T-beam. Cross section of T-beam. Cross section of T-beam. Up to now, this is the discussion for design of flanged beams. I hope you enjoyed this lecture. In next class, we will see the third chapter. That is very easy chapter. For the up to now, what you are discussed here, the in-between steps that we are going to discussing in our third chapter. Okay, thank you. లేదు సార్, తెలీదు నాకు ఏది.